Hey there, welcome back to Combinatorics. In this video, we're going to talk more about sets and probability, and we're going to look at some problems related to poker and the NBA draft lottery. We've already seen some examples of probability problems in the real world. In previous videos, we looked at the NBA draft lottery. We also looked at the Powerball lottery, and we considered some problems about baskets of apples. We also talked about sets in some of the previous videos. With sets, the objects in the set are called elements, and the elements are distinct. The order of the elements in the set does not matter. So if you have a set 1, 2, this is the same set as 2, 1. We also went over some set operations. We talked about unions, intersections, complements, and Cartesian products. And in today's video, we're going to talk more about sets, but we're going to discuss probability all in terms of sets. And like I said, we'll apply the things that we learned today to some more probability problems. From the previous videos, recall that the union of the sets A and B, which is written as A cup B, is equal to the set of elements X, such that X is an element of A, or X is an element of B. Also recall that the intersection of the sets A and B, which is written as A cap B, is equal to the set of elements X, such that X is an element of A, and X is an element of B. So remember that union goes with or, and intersection goes with and. We also talked about complements. The complement of B and A, we write that as A minus B, and that is the set of X, such that X is an element of A, but X is not an element of B. If all of the elements in the sets that we are considering come from some universe U, then we can also just define the complement of a single set. We write that as A with what looks like an exponent C for A complement. And that's defined to be the set of elements X, such that X is an element of the universe U, but X is not an element of A. So we can see a law that you might have seen before if you've studied some logic. And this law we'll phrase in terms of sets. And in order to show this law, we just need to observe that if you have any element of the universe U that's not an element of A union B, then that element must be in both the complement of A and the complement of B. In the other direction, we can see that any element that is in both the complement of A and the complement of B is not going to be in the union of A and B. This tells us that the complement of the union of A and B is the same set as the complement of A intersected with the complement of B. We can do a similar proof with the union and the intersection switched. So if we have some elements of U that are not elements of the intersection of A and B, then those elements must be in at least one of the complement of A or the complement of B. In the other direction, if we have some elements that are in at least one of the complement of A or the complement of B, then they cannot be in the intersection of A and B. And that gives us the other De Morgan law, which is that the complement of the intersection of A and B is equal to the union of the complements of A and B. And if you've seen De Morgan's laws before, you might have seen them in terms of logical propositions. So if we have two logical propositions P and Q, for example, P could be the sky is blue and Q could be the ground is green, then we have not P or Q is equivalent to not P and not Q. The other De Morgan's law is not P and Q is equivalent to not P or not Q. And as you can see, this is very similar to the De Morgan's law in the previous bullet. We have just switched the unions for ors, and we've switched the intersections for ands. We'll define two sets, A and B, to be disjoint if their intersection is the empty set. In other words, if they have no elements in common. We can see right away that if we take the cardinality of A union B for disjoint sets A and B, this cardinality is going to be equal to the cardinality of A plus the cardinality of B, because there's no overlap between A and B. So today, like I said earlier, we're going to think about probability in terms of sets, specifically in terms of the cardinalities of sets. But for this to work, we're going to require that all possible outcomes are equally likely. In these sets that we'll look at, the elements will be possible outcomes. And I just want to emphasize again, in order for these definitions to work with sets, we must require that the possible outcomes are equally likely. So first, let U be the universe of all possible outcomes. Again, I'll emphasize it one more time. The elements of U must be equally likely, so the possible outcomes are equally likely. When we're talking about probability, we will call U the sample space. Now, our events can just be thought of as subsets of U. So the probability of an event E is just going to be the cardinality of E divided by the cardinality of U. Again, to emphasize one more time, the outcomes in U are equally likely. By the definition that I wrote in the last bullet, we can see right away that the probability of an event E is always in the closed interval from 0 to 1. The probability of the empty set is 0, and the probability of U, the whole universe, is 1. Also by De Morgan's laws, we can see that the probability of the complement of E1 union E2 is the same as the probability of the intersection of the complements of E1 and E2. And similarly, the probability of the complement of the intersection of E1 and E2 is the same as the probability of the union of the complements of E1 and E2. All we did to get that was take the De Morgan's laws that we discussed on the previous slide and put a P around them on both sides. So we didn't do any interesting math to obtain this last bullet. We'll define another term. We'll call two events, E1 and E2, mutually exclusive if E1 and E2 as sets are disjoint. In other words, if the intersection of E1 and E2 is the empty set. I'll mention again what we noted earlier, which is that the union of two disjoint sets has cardinality equal to the sum of the sets. And we can use that here with mutually exclusive events to observe that the probability of A union B is equal to the sum of the probabilities of A and B when A and B are mutually exclusive. We can actually say this in much fuller generality. So if we have K events, E1, E2, up to E sub K, and they are pairwise mutually exclusive, then we can say that the probability of the union of those events is equal to the sum of the probabilities of the events. And this is what we will use in at least one of our example problems. We'll also consider some sample spaces in our example problems where the outcomes are not equally likely. Even in those sample spaces, we will still require the rule that we saw in the last bullet, that the probability of the union of pairwise mutually exclusive events is equal to the sum of the probabilities of those events. Now, let's apply what we just talked about to poker. Before we do that, we should probably review the rules just a little bit. In poker, there are 4 suits: the clubs, the diamonds, the hearts, and the spades. Each suit has 13 cards. There's a 2, 3, 4, 5, 6, 7, 8, 9, 10. And there's also a jack, a queen, a king, and an ace. That gives us a total of 4 times 13, which is 52 cards. There might be some jokers in there. We will ignore the jokers. Don't worry about any jokers. In Texas Hold'em, each player is dealt 2 cards. 5 cards are dealt on the table that any player can combine with their own 2 cards. There's also a bunch of other rules in Texas Hold'em involving bids and blinds and the order in which the cards are dealt. We will not worry about any of that. We will only focus today on the probabilities. So we'll suppose that all possible outcomes for the cards that we are dealt are equally likely. In other words, we can assume that the deck of cards is well shuffled enough. So first question that we'll go through about poker is, what is the probability that we are dealt 2 aces? And aces are the cards that have A on them. We need to first define a sample space for this problem if we want to use sets. And if we're going to use sets, we're going to require that the outcomes in that sample space are equally likely. So we could define our sample space to be the universe of outcomes for the 2 cards that we get dealt. And the problem actually told us that these outcomes are equally likely. So it said all possible outcomes for the cards that we are dealt are equally likely. So we have what we need for our sample space. And we can determine the cardinality of our sample space. It's just 52 choose 2, because we're choosing 2 cards from a deck of 52 total cards. The event, E, is going to be the set of outcomes where we're dealt 2 aces. So we need to figure out what's the cardinality of E. We can calculate that one pretty easily by just observing that it's 4 choose 2, because there's 4 total aces and we need to choose 2 of them. Thus, the probability of E is going to be the ratio of the cardinality of E over the cardinality of U. And when we simplify that, we get 1 over 221. And that's the probability that we were looking for, which was asked about in the 3rd bullet on this slide. The probability that we are dealt 2 aces. So now that we looked at one example using sets, let's look at how we can do conditional probabilities with sets. So again, I'm going to emphasize this for probably the 5th or 6th time. All of the outcomes in our sample space are equally likely. So we'll define the conditional probability. P of E1 bar E2 is the way we write it. which stands for the probability of E1 conditioned on E2. And we use the definition that P of E1 conditioned on E2 is equal to the cardinality of the intersection of E1 and E2 divided by the cardinality of E2. Another way to write this, which we saw in last week's videos, is as the probability of E1 intersect E2 divided by the probability of E2. And last week, when we discussed conditional probabilities, we observed that the probability of A conditioned on B times the probability of B is the same as the probability of B conditioned on A times the probability of A. They are both equal to the probability of A and B. And if you see, the symbols that we use to join the events are slightly different in the second and third bullets. So we used ands in the third bullet, the wedge symbol, the hat symbol that you see, and in the second bullet, we used intersection, the cap symbol that you see in the second bullet. The reason why we're using different symbols is because we are representing our events in different ways in these two bullets. So in the second bullet, we are representing our events as sets. In the third bullet, we're representing our events as propositions. However, we can identify the propositions in the third bullet with sets of possible outcomes for which they are true, which corresponds to the second bullet. An example of when we've done this, in the poker problem, we identified the proposition, I got dealt 2 aces, with the set of outcomes in which I was dealt 2 aces. So it's perfectly fine to identify the set of possible outcomes for which the proposition is true with the proposition itself. And when we write two events as propositions A and B, so when we write those events in words instead of sets, we'll write the event that they both happen as A and B. And we'll write the event that at least one of them happens as A or B. On the other hand, if we have two events that we're representing as sets, which we'll call E1 and E2, we'll write the event that they both happen as E1 intersect E2, and we'll write the event that at least one of them happens as E1 union E2. As you can see, and as I mentioned in one of the earlier slides, the and corresponds to the intersection, and the or corresponds to the union. So here is a problem about poker where we can use some conditional probabilities. And the question is to find the probability that you end up with 4 aces using the 5 cards on the table that all the players can use, assuming that you are dealt 2 aces. So we wanted to find a universe of possible outcomes which are equally likely. We wanted to find an event for where we were dealt 2 aces, and we wanted to find an event for where we are dealt 2 aces and we end up with 4 aces using the cards on the table. So we can define the sample space as the universe of outcomes for the 2 cards that we are dealt and the 5 cards on the table that all the players can use. So in the first problem we saw, our sample space just included the 2 cards that were dealt. In this problem, the sample space will include those 2 cards and the 5 cards on the table that we can use and the other players can use. Now we want to see what's the cardinality of that sample space. And in order to find that cardinality, we can count that there are 52 choose 2 possibilities for the cards that we are dealt, the same number that we found in the last problem. And then, depending on the 2 cards that we are dealt, for every possibility for those 2 cards that were dealt, there will be 50 choose 5 possibilities for the 5 cards on the table that all the players can use. This gives us a total number of 52 choose 2 times 50 choose 5 possibilities, and that is the cardinality of the universe U. We'll also define events E1 and E2, which are subsets of U. E1 will be the event that we end up with 4 aces. And E2 will be the event that we are dealt 2 aces. With E2, if we want to find its cardinality, we can calculate that there are 4 choose 2 ways for us to be dealt 2 aces. And then for any of the ways that we can be dealt 2 aces, there are 50 choose 5 possibilities for the 5 cards that are dealt on the table that any of the players can use. Thus, we can conclude that the cardinality of E2 is the product of 4 choose 2 and 50 choose 5. We also want to get the cardinality of E1 intersect E2. The cardinality of E1 doesn't really matter if we're trying to get this conditional probability. So we could calculate it if we wanted to, but we don't need to. And since we don't need to, we won't. So the cardinality of E1 intersects E2. In order to figure this one out, we can first do the same thing we did with the cardinality of E2. We can see that there are 4 choose 2 possibilities for the 2 aces that we are dealt. Now, if we end up with 4 aces, that means that in the 5 cards on the table, the 2 aces that were not dealt must appear in those 5 cards. So we already know 2 of those 5 cards. That means that there's only 3 cards out of the 5 on the table that we have any choices for. And for those 3 cards, we can choose from any of the 48 cards that are not aces. We're choosing 3 of them, so we get 48 choose 3. So the cardinality of the intersection of E1 and E2 is just 4 choose 2 times 48 choose 3. Finally, we finish the problem by calculating the probability of E1 conditioned on E2. We can plug it into the formula that we discussed on the previous slide. It's just the cardinality of E1 intersect E2 divided by the cardinality of E2. And this gives us, when we simplify, 2 divided by 245. Let's do one more example problem with conditional probability. We've seen a similar problem before, but I got a lot of questions about that one. So I thought we should do one that is pretty similar, but a different problem. Before we go over this problem, let's review the NBA draft lottery and its rules. Recall that the NBA draft lottery involves 14 NBA teams. These are the teams with the worst regular season records in the previous season. In other words, these are the teams that did not make the playoffs in the previous season. I got some questions about why teams want to get high picks in the draft. Well, the reason why teams want to get higher picks is so that they can choose the best basketball players that declare for the draft that year. So each player can only go to one team. Some players don't get picked. But if a team wants to get the very best player for their team, then they'll hope to get one of the top picks so they can take that player before some other team takes that player. For example, if a team gets lucky enough to win the first pick in the NBA draft lottery, they can choose the player who they consider to be the most valuable to their team. So that might be the best player in the draft that year, or it could be a player that they think that they can make a really good trade for, or a good trade with, and obtain better assets using that player from another team. And as we saw when we discussed the draft before, the rules of the draft lottery are based on probabilities and conditional probabilities. So the order of the teams that they get to select in the draft is just determined by a bunch of probabilities and conditional probabilities. Let's go over how these teams get to select their picks in the draft. So we have a total of 1,000 combinations that get split between the 14 teams, but they're not split equally because, of course, 1,000 is not divisible by 14. So the 3 teams that have the worst regular season record from the previous season, they each get 140 of the combinations. The 4th worst team from the previous season gets 125 combinations. The 5th team, 5th worst, gets 105 combinations. The 6th worst team gets 90 combinations. The 7th worst gets 75. The 8th worst gets 60. The 9th worst team gets 45 combinations. So you can see the combinations are dropping fast as the teams get better. The 10th worst team gets 30 combinations. The 11th worst team gets 20. The 12th worst gets 15. The 13th worst only gets 10. And the 14th only gets 5. Now let's talk about the experiment that's performed that determines which team gets the first pick, which team gets the second pick, and then the 3rd and 4th picks. So for the first pick, one of the combinations out of the 1,000 is drawn uniformly at random. The team with that combination gets the first pick. That's all that happens. Now for the second pick, the same experiment is performed. Another combination is drawn uniformly at random. However, it's possible that that combination that gets drawn for the second pick might be a combination that belongs to the team that got the first pick. If that happens, if we draw a combination for the second pick that belongs to the team that got the first pick, we discard that combination. And if we draw a combination that does not belong to the team that got the first pick, then the team with that combination gets the second pick. So this process is equivalent to throwing out all the combinations of the team that got the first pick and choosing from the remaining combinations for the second pick. We repeat this with the third pick. In other words, we throw out all the combinations for the teams that got the first 2 picks, and then we choose a combination for the third pick. And then the 4th pick, very similar. We throw out all of the combinations for the teams that got the first 3 picks, and then we choose a combination for the 4th pick. But then at the 5th pick, it totally changes. So for the remaining picks, the teams that did not get selected for the first 4 picks will get draft picks in reverse order of their regular season record. So in other words, they get draft picks in order of worst regular season record. So now let's do a problem with some conditional probability. And again, we've seen a problem similar to this before, but it seemed like it would be good to discuss another problem like that. So this problem is to find the probability that the 14th worst team by regular season record gets the second pick in the draft. And this last season, the 2020 season, the 14th worst team was the Grizzlies. So the Grizzlies almost made the playoffs, but they lost their play-in game. Now, if we want to find this probability that the 14th worst team gets the second pick, it might be tempting to define the universe U of outcomes as combinations that are drawn for the first 2 picks. Now, you can probably see that there's going to be an issue with this because I wrote it might be tempting. And the issue is that these outcomes are not equally likely. How can we see that pretty easily? Well, for example, we can fix some combination, which I'll call A, belonging to the worst ranked team, which was Golden State in the previous season. We'll also pick a combination B belonging to the second worst ranked team and a combination C belonging to the 14th worst ranked team. We fix A, B, and C. So A, B, and C are fixed combinations. Then we can say the outcome where we get A on the first pick and B on the second pick is going to have probability equal to 1 over 1,000 times 1 over 860. The 1 over 1,000 is the probability that we get A on the first pick. And the 1 over 860 is the probability that we get B on the second pick, conditioned on us getting A on the first pick. Now, here's another outcome. The outcome where we get C on the first pick and B on the second pick, I claim this one has probability 1 over 1,000 times 1 over 995. The 1 over 1,000 is the probability of getting C on the first pick. The 1 over 995 is the probability of getting B on the second pick, conditioned on the fact that we got C on the first pick. And you can see that the second probability, the 1 over 1,000 times 1 over 995, that's going to be less than the first probability, which is 1 over 1,000 times 1 over 860. So unfortunately, these outcomes are not equally likely. The funny thing is that if we assume they were equally likely and we did the calculation using that, we still get something that's not too far off the right answer, but it is somewhat wrong. So let's try to get the answer that is exactly right. So we're going to have to go about this problem differently than the ones that we just did. We cannot use a universe U of equally likely outcomes if we define our outcomes as these combinations for the first two picks. So what we'll do is we'll use some conditional probabilities. And we'll also use the fact that we discussed about the probability of the union of mutually exclusive events. Now, why do we want to use conditional probabilities? Well, the reason why they're useful here is because the rules of the NBA draft lottery, they actually spell out what the conditional probabilities are. So the rules tell us what these probabilities should be, and it's simpler to find these probabilities and then figure out the probability that the 14th worst ranked team gets the second pick by combining these conditional probabilities with some other probabilities. How are we going to combine them? Well, here's what we're going to do. So if we want to get the probability that the 14th worst ranked team gets the second pick, we're going to calculate these probabilities of AI and B, where we need to define the AI, though I actually defined these in the slides from last week. So AI is the event that the ith worst team gets the first pick, and B is the event that the 14th worst ranked team gets the second pick. So we're going to calculate the probability of AI and B for each I from 1 up to 13. And then we'll just add up those probabilities. Before we do that, let's talk a little bit about why that works. So we're going to use the fact here that the events AI and B for I equals 1, 2, up to 13 are pairwise mutually exclusive. So none of those events have any intersection with each other. Moreover, we can say that the event B is equal to the disjunction of the events AI and B for I equals 1 up to 13. In other words, we can say that if B is true, then AI and B must be true for some I between 1 and 13. And moreover, if AI and B is true for some I from 1 up to 13, then we can say that B must also be true. So B is actually equal to that disjunction from I equals 1 up to 13 of AI and B. Another thing I'll note here is that this disjunction runs from I equals 1 to 13, not I equals 1 to 14. Why do we not include 14 in there? Well, let's think for a second about the event AI and B when I equals 14. AI and B when I equals 14, in other words, A sub 14 and B, is stating that the 14th worst ranked team gets the first pick and the 14th worst ranked team gets the second pick, as we saw in the rules of the NBA draft lottery, the same team cannot get the first 2 picks in the lottery. It's possible for a team to obtain the second pick and the first pick through trades, but the lottery will not give the same team the first 2 picks. And we're only talking about what happens in the lottery, nothing about trades. So this is why our disjunction runs from I equals 1 to 13. I'll mention again, which I mentioned in one of the earlier videos, is that disjunction means or, conjunction means and. So because B is equal to the disjunction of these events, AI and B, and because those events are pairwise mutually exclusive, we can conclude that the probability of B is equal to the sum of the probabilities of the events AI and B for I equals 1 up to 13. So that's what we claimed in the previous slide or previous bullet, and this bullet is just some reasons why that's fine to do. And now that we see that it's fine to do this, let's actually calculate the probability that we're looking for. So we'll start with I equals 1. And just to have the definitions on this slide, AI again is the ith worst team getting the first pick, the event of that, and BI is the event that the 14th worst ranked team gets the second pick. So let's say I equals 1. Then if we want to find the probability of AI and B, we can use the fact that the probability of the conjunction of 2 events, probability of AI and B, is equal to the probability of AI times the probability of B conditioned on AI. And that means that we just have to calculate probability of AI and probability of B conditioned on AI. Probability of AI, that's just the probability that the first team gets the first pick. And that's the number of combinations of the first team divided by the total number of combinations. So it's 140 over 1,000, which gives us 0.14. Probability of B conditioned on AI is just the probability that the 14th worst team gets the second pick if the worst team gets the first pick. If the worst team gets the first pick, all of the combinations of the worst team are thrown out for the second pick. The worst team had 140 combinations. So if all of their combinations are thrown out for the second pick, that leaves us with 1,000 minus 140, which is 860 combinations. So the probability of B conditioned on AI is the number of combinations for the 14th worst ranked team divided by the total number of combinations for the second pick. And the 14th worst ranked team, as we discussed, only gets 5 combinations. And the number of combinations for the second pick that are possible, if the worst ranked team got the first pick, we already said that was 860. So the probability of B conditioned on AI is just 5 over 860. So we multiply 0.14 times 5 over 860, and we get 7 over 8,600. We do the exact same thing for I equals 2 and 3. So what I just said for I equals 1, the exact same argument works for I equals 2 and I equals 3. For I equals 4, we're going to do the same thing, but now the number of combinations is slightly different than it was for I equals 1, 2, and 3. So again, probability of AI and B is the probability of AI times the probability of B conditioned on AI. In this case, when I equals 4, we know that the 4th worst ranked team gets 125 combinations. So the probability of A4 is going to be 0.125. The probability of B conditioned on A4, we're still going to have 5 in the numerator, but our denominator now is going to be 1,000 minus 125 instead of 1,000 minus 140. Because in this case, we're taking out the combinations that belong to the 4th worst ranked team, and that team only had 125 combinations. So the 4th worst ranked team only had 125. So we're subtracting 125 instead of 140 like we did in the previous one. So we end up with 0.125 times 5 over 875, and that simplifies to 1 over 1,400. For I equals 5, it's very similar. We just get 0.105 times 5 over 895. The 0.105 being 105 over 1,000, the 895 being 1,000 minus 105. And this simplifies to 21 over 35,800. For I equals 6, again, very similar. We get 0.09 times 5 over 910. The 0.09 is 90 over 1,000. The 910 is 1,000 minus 90. This simplifies to 9 divided by 18,200. For I equals 7, we get 0.075 times 5 over 925. The 0.075 is just 75 over 1,000. The 925 is just 1,000 minus 75. And this simplifies to 3 over 7,400. For I equals 8, we get 60 combinations over 1,000 combinations, which gives us that 0.06. And then for the denominator of the fraction, that's 1,000 minus 60. I equals 9, similarly, we get 45 over 1,000, giving us the 0.045. And the denominator, we get 1,000 minus 45, which is 955. And this gives us 9 over 38,200 when we simplify the product. For I equals 10, we proceed the same way, but now we have 30 combinations, and we get 3 over 19,400. For I equals 11, there's only 20 combinations. We get 1 over 9,800. For I equals 12, with only 15 combinations, we get 3 over 39,400. And there's only one I left to do because we're only going up to 13. For I equals 13, we get only 10 combinations. So 10 over 1,000 is the 0.01. And then 1,000 minus 10, we get the 990. And this leaves us with 1 over 19,800. And all we have to do is add all these numbers together. We sum them up, and that gives us approximately 0.00558. So we can say that the probability that the 14th worst ranked team gets the second pick is approximately 0.56%. That brings us to the end. Thanks very much for watching. See you next time.